All right, we'll get started here in about 30 seconds. All right, we're going to go ahead and get started. In between the sessions, but for that BFA that was coming back around, we showed as increasing your mixed liquor concentration, and basically the aeration basins became storage. And what kind of happened in the break is we were discussing what actually happened on the liquid side of all this solids capacity issues. What happened on the liquid side? Besides building up mixed liquors, what happened here? And the big thing that happened here was BFAs coming in. We're normally in the probably 60 to 70 milligrams per liter. That's normal coming into their selector. Steve, what were they coming in? We were over 100?
There's more than the selector.
Yeah, so essentially what happened, all that extra VFA, they were normally in the 60 to 70, they had 100. All that VFA would normally get sucked up in here. What started happening was VFAs were bleeding into this zone here. Does anybody remember what kind of DO we had in this first zone? We had a 0.25 DO, so they started to see filament growth in the form of zooglia. And basically what happened is their SBIs went from SBIs of 50 to 100. They had blankets taller than me. And that's one of the reasons when I said they couldn't take deep flows. It was because of this VFA coming in, not only impacted the mixed liquor to manage it, but really it started to impact settleability. And increasing air in this zone, they still couldn't catch up to it. There was just so much VFA pouring out of that selector because it's overloaded. That starts to get into kind of some of the images Paul showed on the industrial side were very extreme images of high soluble loads. But I mean, you can kind of start to see what happens when you get that high soluble load and it's overloading your system. When your bacteria are happy, your heterotrophs. Paul talked about making polymers, those biopolymers. Polymers are made when bacteria are happy. Polymers are the glue that help flocks stick together. And so polymers are good. But when bacteria are happy and they have a lot of carbon, they just produce polymer like gangbusters because they don't need to grow. They're already growing as fast as they can. They've already maxed out their growth rate. So they're just taking all that carbon and making a bunch of polymers. And so really wanted to close the loop on the liquid side of this and on the impact of it, of that BFA. All right, so now we're gonna finish the day here talking about kind of finishing up on nitrogen. So this will be your full-on nitrogen kind of clinic here. We ended with this large recycle stream coming back. We have that 3,000 milligrams per liter, about 15 to 20%. And what are the impacts of increased ammonium coming back to our process? So alkalinity. If we're already short on alkalinity, that extra alkalinity can really start to decrease our pH. We can start to have pH issues. I know Cruz sometimes has pH issues. I know there's some plants at North Texas can run into some pH issues, and that's really because of this extra nitrification. This extra nitrification that's coming around is going to start to decrease that alkalinity. I think Cruz going out of the back end of the plant to above 100 milligrams per liter alkalinity. I think now you're getting around to 190. You're starting to get the alkalinity start to tip down, and usually you're starting to get kind of on the edge of not having enough buffer capacity. When you're getting closer to like 75 milligrams per liter of alkalinity, rule of thumb is 50, you start raising a red flag. You're getting 50 at the outfluid, you're probably have a lot of buffering pH issues in the plant. Aeration energy, more nitrogen means more air is required. You got to feed it. Biological phosphorus removal. Now we have 20% more ammonium. That probably means we have 20% more nitrate. That nitrate then comes back in our process. And it's coming back to the head of the aeration basin, which could disrupt BioP. So all this alkalinity starts to have impacts. And then the last one is capacity. You might just not have the actual processing capacity of your system to handle it. So what do you do about this? If you can't handle it, if you have BioP and you want to make sure you have consistent performance, how do we treat recycled ammonia? Sidestream. We start looking at sidestream management. So we're looking at doing a targeted point. We're going to put in a separate process to treat it because we can do it in a small footprint and we can do it energy efficiently and not have native carbon. The other big thing is if you don't have enough carbon to denitrify all that nitrate, you're kind of your ratios start to get thrown out of whack. So if normally you're getting denitrification, let's say you had let's say your ammonium going out is usually 9 milligrams per liter, or nitrate, sorry, 9 milligrams per liter. You're getting some denitrification. So coming in, maybe I had 25 ammonia. So this is in, out, fully nitrified, and that's all nitrate. If I'm managing that, I'm getting my BioP to work, but then I increase this by 20%, so we increase this to 30 milligrams per liter. And the reason I was able to get the 25 to 9 is because I did denitrification, right? I used carbon to denitrify. Let's say I'm out of carbon, but now I'm taking all of that 5, and now I'm at 14 milligrams per liter of nitrate going out, which means that I'm increasing in my anaerobic zone here. This is my selector zone for BioP. Now I have 5 more milligrams per liter of nitrate coming into it. That nitrate has a carbon demand associated with it. And that carbon demand gets fulfilled before the BioP works. BioP is second. The PAOs, and Leon will jump into this a lot tomorrow. But that ammonium load could be a very significant load in terms of BioP stability, and why you want to kind of start managing it, maybe not in the mainstream, especially if you're running out of carbon. So a couple of things we'll talk about is deammonification, and another one is post-aerobic digestion on the side stream, and really focusing on the nitrogen cycle here. What is the goal? The goal is obviously to remove nitrogen in the side stream. And we can do it through traditional nitrification, denitrification. We want to mitigate these impacts on alkalinity, nitrate impact, and aeration demands. And kind of here's our two technologies. And we talk about these transformations. Paul covered them a little bit. But we've been mainly talking about is this traditional pathway. Go ammonium to nitrite, nitrate to nitrogen gas. And really what these two technologies are focusing on are shortcuts. They're using shortcuts of this triangle. So the first one is really nitrite shunt. So basically, can I make it so that my AOB are only going to nitrite? And then I take that nitrite and I denitrify it. So that's the pad pathway. So it's doing a shortcut. So what are we saving here? We're saving 25% air demand, and we're saving 40% carbon. Because I can do a shortcut nitrogen removal process. That's the pad process. And that still requires carbon. No, we didn't get rid of all the carbon yet. Deammonification is the one kind of that's the other alternative right now. And deammonification is essentially using Anammox bacteria, and you're taking 50% of it to nitrite. You're not even touching 50% of the ammonium. And you're taking both these in a mix, and this Anammox bacteria makes nitrogen gas without any carbon. So they have a mechanism that basically they're a very low energy organism. So when we talk about SRTs of this organism, this Anammox organism, we're talking like normally we're talking 10-day SRTs in aeration basins. We're talking 60 to 100-day SRTs for these bacteria to grow. They're just very slow growers because there's very little energy in this business. Like when you think about like electron transport, ATP that Paul talked about, there's not a lot of ATP to gain in here. And so they're living on very low ATP amounts. So what does this deammonification process look like? Essentially, what it is we're looking at doing it on the filtrate. So you're putting the deammonification process on the filtrate before it comes back around. Focusing in this area before you send it back to the head of the plant where it gets larger. The deammonification process, what we're really looking at here is taking our centrate or filtrate, has some kind of EQ, and then you're going into this reactor where we have our Anammox bacteria that we're looking at keeping stable. And so this is where we're growing those bacteria. And I'm going to jump up to this slide here. these bacteria are these red ones here. Large granules. It's kind of like 2 millimeter granules that are growing. I mean, so keeping them in a reactor is actually very easy. They settle very well. They're hard to wash out because they're so dense. Some of the technologies actually look at having these grow on media. How many of you guys have seen like MBBRs, where it's like this plastic media that floats in the aeration basins? We got one here. They grow on that media, and you can't lose the media then. And your SRT can be infinite with the media. So you're either growing this granule form, or we're growing on a media to essentially get that deammonification. And that's how we're getting past that. So we're growing. I want to kind of emphasize this again. We're growing AOB, growing the first step. We're growing AOB, and we're growing Animox. So what would be some of the challenges here? I want to get nitrite, 50% nitrite. I don't want to nitrify at all. I just want to get 50. So, and I only want AOB. Where am I going to get what? How am I going to stop it? Oh no, you AOB make it. Basically, you're stopping it before it goes to nitrate. You're stopping this. You're breaking this cycle.
The original source.
Oh, this is coming from our digester. Sorry, this is Sidestream application. The ammonium's coming in from the digester. And basically, we're taking 50% of that ammonium and making nitrite. What are some of the challenges you foresee? Kind of think about your traditional nitrification systems in the mainstream. You're doing this process. Has anybody ever tried to stop here? You don't want to, first of all. Stopping here is very difficult in the mainstream. You're basically trying to say, I want to stop growing NOB, but I want to grow AOB. So I want to pick AOB over NOB. It's a very difficult process to control in the mainstream because of temperatures. Temperatures we're talking about here are 35 C, so you're 100 degrees Fahrenheit, versus your wastewater is like 60 degrees. When we start talking about 100 degrees Fahrenheit, the growth rate of these two start to deviate. And so we can actually, it's only a one-day SRT we run in these reactors. And that way we can maintain AOB at a one-day SRT, but NOB get washed out because of the growth rate. And I kind of want to draw that growth rate out real quick. I'm going to show you a good example of what it kind of looks like. If we were to have, if this is temperature, and this is rate. So as the temperature goes up, this will be this one like this. Remember these curves, you get very familiar with these curves. So this is let's use this as our NOB. That's the second step. And then here's our AOB. Like they're competing. And then way out here, AOB separate. So here's where you're typically operating in the mainstream. So let's say this is 60 to 80 F out here. Out here, we're at 100 plus F. So you can start to see how you deviate here. But here, if you were to try to say, I'm going to use SRT to distinguish between those, you're trying to control an SRT of 6.2 days versus 6.3 days. Anybody do that? Most of us can't control between 6 and 7 days. So trying to control decimal is impossible. Even controlling 5 days sometimes is difficult. So you're not controlling to a decimal. But out here, you're talking about having like plus 1 day difference in growth rates. So if I run a 1 day SRT out here, I can actually stop this from growing and being present, but keep these. So that's one thing they're doing. You're managing HRT and SRT essentially to stop it here. What else might be difficult about this? I only want 50% of it here now too. I don't want these guys to eat it all. So you got to have a sensor in here to read ammonium. Because essentially you're saying, okay, I want 50% of it, and I want 50% of this. So I've got to have equal parts of each to do this. So you essentially have sensors in there controlling air. So your air, if you're looking at like an air cycle in these, it's probably going to do like this. Because it's trying to do just enough air to get 50%. And then lastly, This is aerobic. DO is actually inhibitory to Anammox bacteria, the red bacteria. So you start like building on the layers of complexity here. Deammonification, this whole process here, essentially what you end up having, the bacteria, the way they set themselves up, it's kind of neat. We want to have aerobic, and the reason the granules are so big is because of this. So let's say that's our granule. Blue. No, I gotta use red because they're red bacteria. All right. So in here, here's our Anammox bacteria. And then basically this whole thing, this granule, is filled with a bunch of AOBs. So you can kind of see out here we have 2DO. That's an example. Maybe let's call it 1. It's going to be lower. 1DO out here, because the AOB, they like that air. They like that. They want to be aerobic. They need air to do their processing. So they're taking an H4 out here. As they go through, they're converting that to NO2, which these guys want. But these guys don't want DO. So as you go through this granule, DO actually decreases too. So 1DO out here might be a 0.1 DO in here. Because you start getting into diffusion. So biofilms and granules, you start getting into diffusion properties. But as you go deeper and deeper in here, you get different environments. And this also happens in the mainstream. Like when we talk about granulation or densification of your sludge and you have good flock, what you can also have in this case, if we just use aeration basins, well, a lot of times you're going to have almost 3 layers. So out here, you're going to have like your OHOs, your heterotrophs. They're doing maybe carbon work, and there you have AOBs. You have OHOs in here. This middle one is doing denitrification, and it's anoxic. This is aerobic. And here's where our PAOs are, in the middle. It's anaerobic. And you can start to see how granules and good bacteria, like if you form a well-settling flock, you can actually, remember those slides that Paul was showing up there with the different bacteria highlighted different colors? They actually look at where they're at in flocks. They tend to get themselves into this area because they all like different parts, different environments. And by having a nice flock, a nice granule in your mainstream system, you start to create these different environments where we're doing aerobic activity, we have anoxic activity, and we have anaerobic activity. And that's really where Cruise leverages that low DO. Because they might have 0.5 DO out here, which means they can get to 0 in the middle. But if I have 5 DO out here, this isn't going to be anaerobic. That DO will go all the way in the middle. So that's where like that low DO starts to have better performance because you can start to create these stratified layers. But 5 DO, it's hard to make it. All of this is going to be homogeneous because the DO is so high. It's all going to be aerobic. You're not going to have these little micro environments. So low DO really starts creating micro environments. Getting back to what I was talking about though was this Anammox bacteria is taking advantage of microenvironments. It's protecting itself in a layer of AOBs and essentially being able to, because it does not like that DO. And so it has to take this nitrite and ammonium and make this nitrogen gas without DO and without carbon. That's the benefit. And for how complex it sounds, it's actually a very stable and like pretty straightforward process once it gets going. It sounds complex, but these bacteria, once they grow, the slow growing bacteria, remember I said use with very low ATP, but slow, here's a general rule of thumb. Slow growing, slow dying. Quick growing, quick dying. So they don't die quickly at all. Their death rate is very, very low. And in fact, if you see these, when they first brought them over to the US, the first plant that brought them over to the US, brought them over and they're like dried almost. And you just throw them in the water and they like basically hydrate again and basically come back. And they sat in customs. One of the plants that we worked at sat in customs for like 3 months. They got caught in customs. They had bacteria sitting there. They brought them to the aeration basins. Nobody thought it'd work. Dumped them in. A couple days later, they came back out. So the when you have a slow growing thing, it's slow growing because there's not a lot of energy it's harnessing. This process here doesn't have a lot of ATP available, so they don't need a lot to grow. It also means they don't need a lot to stay alive. They're not using a lot of energy, but that's also why they need a 60-day SRT. So it's a very stable process. It may sound complex, but once you kind of get it going, it kind of just hums along. And so that's really kind of the full nitrogen picture here. We've got our traditional pathway. We have our shortcut. The one thing I want to close on a little bit, and I know Paul talked about inhibition in the mainstream. I want to talk about this nitrite shunt a little bit. In the mainstream, we don't want this. I mean, we would want it if you control it. What is it? What if this is happening in the mainstream? What's happening? Nitrite lock is what I heard up here. What's nitrite lock? You got inhibition. For whatever reason, this bacteria is getting impacted. And usually when you have an inhibition event or an upset, if you start seeing nitrite in your process, start digging further, because there's likely something else going on. These bacteria are sensitive, and they're the first ones to kind of raise the flag if something's wrong. So if you see nitrite in your mainstream process, you're likely having some kind of inhibition to this bacteria here. It's very hard to actually control and not have them grow in the mainstream. But if they're not growing, that means something else is happening, and you have nitrite accumulation. For any plant here, how many plants have chlorine disinfection? Quite a few. What does nitrite and chlorine look like? Or not look like? What's the demand change?
5 to 1.
5 to 1. So for every 1 milligram per liter of nitrite going on your plant, 5 milligrams per liter of chlorine going on your plant as well. 5 times as much chlorine if you have a milligram per liter of nitrite going out. So if you start to see, if you don't measure nitrite, because nobody needs to measure nitrite every day. You should not be measuring nitrite every day for process performance. If you see a chlorine demand spike, go measure nitrite. Because it could be your chlorine went up because you have nitrite. Nitrite went up because maybe something's wrong. And it could be that you turned your DO down. Maybe your DO is not working and you were normally operating a 3 DO and you turned it down to 4.5 DO, and that's too low. You didn't give them time to acclimate. And it could be an inhibition event. There could be a lot of things. But as soon as you identify, all we're doing from an operator standpoint, we're looking for indicators. We're always looking at our process indicators. We have DOs, we have airflows, we have chlorine demands, and we're trending things. I think I heard Carl here say, I love looking at the trends. Trending is what we should all be doing. If you're looking at trends and something is off trend, ask why it's off trend. Is it, oh, hey, we had to shut down that piece of equipment, that's why the trend's off. Okay, that's fine, we can move on. If it's a trend you can't explain, you should try explaining it. You know, if it's a trend you can't explain, start thinking about what could cause that trend and start digging in further, and then have that inform sampling. I guess the one thing I would say is sampling is good, but aimless sampling is not always the best thing to do either. Collecting samples without collecting samples, you don't know what those samples always mean, and sometimes you just quit doing it. See, 2 hands, I'm gonna go up here first.
Also, you go nitrite lock if you don't have enough alkalinity.
Oh, that's another alkalinity. So this is one thing that I experienced here, went too low. And basically the first thing that stops is the second step here. So you have nitrite accumulation. I don't know if you saw that at Rowlett or not. Yeah, well, I don't know if you saw nitrites, but you have UV there now, don't you? Oh, it's chlorine. Oh, so you might have seen, yeah, when the MBR was on, you might have seen the nitrite come up there. Paul?
So we're tested NO2 and NO3 4 to 6 times per day. And we're doing that because we're running such a fine line right now. You know, we can have 0.5 loading.
Yep.
And knock our chlorine dose rate down into 5s, even 3s for dose rate.
Yep.
But if that nitrite starts creeping up, even with 0.5, 0.7, 1 whole part ammonia, we're 7-8 times chlorine dose rate.
Yeah, it spikes pretty quickly.
Really have to watch that close.
So I would, you should sample to inform what you're operating at. I don't mean that you shouldn't sample, Paul. That's a,
Well, no, you said like you only have to do it every couple of days.
depending on what you're trying to do, you should be sampling to inform your operations. But in terms of like taking a nitrite sample every day or a process troubleshooting one, use indicators and trends as much as you can. You're always going to be measuring TSS. We're always going to be taking ammonium samples. We're always going to be doing some of these things to make sure we're monitoring our process. But you don't need to add some of them as frequently as possible. Like you don't need to have it be busy work. Watch those trends and inform where you're sampling and why you're sampling for it. You should know why you're sampling. Paul just explained why he's sampling.
Yes.
He didn't say I'm sampling because I was told to. He explained, well, I'm doing this because I'm trying to control my chlorine dose. He's trying to bleed ammonia to make chloramines. That's what he's trying to do. And so he's trying to reduce his chlorine dose by having ammonium bleed through. But that's a balance. But he knows why he's doing it.
So
Yeah, SO2?
teams are harder to.
I don't know. What is your SO2?
Well,
I've never heard of complain about it. What's that?
Yeah, we can dose less SO2 as well. Yeah.
Any questions on that?
What conditions select for the granules?
What conditions select for the granules? This is good. It's a good question that we didn't really, we covered a little bit. So when we talk about, think through, so I'll draw this graph first. This is F to M. This is going to be grams of SCOD per gram of VSS. This is going to be granule size. Essentially, our F to M, so it's grams of soluble COD. What's really impacting our granule growth is our VFAs and that readily RVCOD. And so when we start talking about that, we have this F to M gradient curve. So if we're at a low F to M, remember we showed that, so let me flip back to that as we talked about it. Amazing how many slides you go through. All right, here we go. So this good flocks, a lot of plants that are operating day in and day out with an SVI of 75 to 110 are probably in this range here. They have good flocks. Settles well. I think most plants probably would say they have good flocks. Anymore, you don't hear a lot of plants say they have 150 SVIs. They're out there, trust me. But in general, you don't see that as much anymore. Getting that granules is increasing that F to M. And really, it's this F to M. A lot of times people measure this basin. So I'm talking about F to M. Let's say we have a basin with a selector zone in it. So how could we calculate F to M? What's our F to M is food, right? To microbes. And basically we're calculating our food is what's coming in. That's where we're just doing pounds of, let's say, so pounds COD per day coming in. That's our food. How are we calculating microbes? MLVSS in what? How do I just do? Am I doing milligrams per liter? Or am I doing pounds? Pounds. How am I getting my pounds? Milligrams per liter. Capacity of the basin? The volume of the basin. Volume of the basin. So I want to get how many pounds are sitting in here. Because basically I'm applying this many pounds to this many pounds. I have all these pounds sitting in here waiting for that food. And I want to know what my F to M is. So I can calculate my F to M as what? The whole basin? Just the blanket. So if I calculate the whole basin, that's assuming like it's all mixed. Is it mixed? Our F to M actually looks like this. It's really high here, and it's going to decrease like this. Because it's a plug flow system. All our food's up here. So really what you need to start focusing on, and when we talk about granule formation, is we want to know what our F to M is up front in those selector zones. We want to start getting into this selector, this F to M, and it's very small. I don't know how small it is on your on your slides, 0.2 to 0.4 grams of RBCOD per gram of VSS. And you can also, there's one that's grams of COD per gram of VSS. But essentially, if you look at this range, this is 0.2, this is 0.4, and it's a fine line. And some of it can be tough to control. But essentially what you're trying to do is control that F to M, because as that F to M increases, you essentially get this like granule size increase. The higher we can get that F to M to a point where it breaks.
Specifically at the front of the slide.
At the front of the selectors. Yep. And to me, the selectors, you can have aerobic selectors, so you can aerate your selectors. You can have anoxic selectors, and you can have anaerobic selectors. And so really what you're trying to do is have this high FTM gradient. You want it to be steep. You want it to be this feast, because essentially what you're trying to do, the bigger your granule can get, the higher the FTM. So if I were to do, let's say I have a granule of this size. Let's say I have a 0.4 grams of COD per gram of VSS. That can diffuse into the middle of the flock. But if I'm at 0.2, so let's say that's going, I don't know, let's say it's going in 1 millimeter. It's able to diffuse in 1 millimeter. But if I'm at 0.2, I can only go half that. So now my granule's got to be half that. Because if you can't go into the middle's not getting food. What happens to something that doesn't get food? It dies. The middle of your granule is dead, falls apart. So your granules are self-regulating to a degree. They're self-regulating because they're going to fall apart because they can't grow any bigger because the middle will run out of food. Typically, EBPR BioP facilities are going to see better, denser granules. Because in the middle of that granule, those PAOs, they like to sit in the middle of that granule. Because they like that anaerobic. They like the anaerobic process, like the anaerobic environment of that middle, and they're dense bacteria. PAOs are dense bacteria. So imagine putting like a nice dense rock in the middle of your bacteria. So you can have granules without EBPR. Usually EBPR, you're going to have denser granules, and they're going to be better separated. So I mean, in terms of forming that, then what you're controlling in your process is one, design. So I hate to say it, if your reactor is a complete mixed reactor and it's square, you don't get this gradient because it's all the same concentration. So sometimes you're going to be hamstrung at your plants to a degree on what flock you can make if you don't have well-sized selectors and aeration basins. The next thing is SRT, because I can control this microbes. So you're balancing your SRT with your nitrifiers because they're going to set your minimum. But then I'm going to try to really hone in on my F to M with my SRT here to try to get that. And that's what TRA did when they had all that BFA coming back around. That they started increasing the mixed liquor. Their F to M ratio was getting way over 18. It's like they basically tried to inch it down. That's where they ended up at that 7,000 milligrams per liter. They're still only at a 10 or 11 day SRT. And it is mainly because all that load was coming in and they were overloading the F to M. So you're able to control it with, let's see here. So control would be, well, design, you can't control that. SRT, if you have any way to, some plants have ways to, feed all of the RAS to here or all of the PE to here. Some plants have another zone, and Dan, I'm referring to you. Have another zone where some of that RAS can go to here. Then you're starting to mess with how much that food is and where that PE is going. And again, you're still limited by how much can I turn it up or down. There's still controls that you're going to be limited by. So you can start controlling the F to M here with things like that. Not a lot of plants don't have that ability. That's pretty unique. I think Benton Creek has it. Wilson Creek. He's said getting it at Mountain Creek. That's a pretty rare one. The only other thing you can really do, some facilities have step feed. If it's too high, like if you're way out here, you can step feed it down the basin to change that up down. And then the last one I want to go over is this. If you have an aerobic selector, so let's say you don't have a selector. Some plants are just aeration basins. This is where I know this plot may, or this like figure may be a lot to understand. But like, if we have the, coming into here, and we have a high soluble COD, and it's basically like an aerobic selector in our first zone. Aerobic selectors are a little harder to manage. You've got to correlate that DO to make it so that you're forming granules and you're forming good settling flock. But a lot of plants, you're going to be required, I've done the math on a lot of plants, you're going to be required to hit like a 3 or 4 DO in the first upfront zone. Most plants can. Just too much demand up there for an aerobic selector. You'd have to really design to hit that. Most traditional nitrification plants that don't have like just an aeration basin, the density diffusers up here is high enough to hit a 3 or 4 DO. So you're going to have some degree of bulking, which is going to start to decrease. You saw the different kind of images that Paul had, where some have different levels of filaments. Those filaments are going to start to say, okay, that's the difference between an 80 SVI and a 100. I wasn't able to control it as much. I have more filaments than in other plants. But really, it's filament control is kind of, in my mind, a little bit of the easier one. But getting the denser granules it can be pretty tough to get a very dense granule. You need to have the right food, high BFAs. Texas usually has high BFAs. So your design's got to be able to kind of be flexible and meet that. So. Did I answer that question?